kasih Hidayah. Now I would like to invite Yoong for his project Improve to Derivative Range-Kutta Methods for Solving First Order Ordinary Differential Equations.
Kira. Kasi pang
Also, a very good morning to examiners and my fellow friends. So, my research is about proposing an improved two-derivative Range-Kutta methods for solving first-order ODEs. So, this will be all the contents that we'll be going through today. So, we'll just start with introduction. So, in our paper, we are just focused on solving first-order ODEs. So, it has in this form. So, there are many numerical methods to solve, like Euler methods. So, my method is based off Range-Kutta. And there are a few, the classical Range-Kutta methods, and then we have improved RK methods. So improved RK method is a two-step method, while the classical is just one step. And then another one is two-derivative RK method, so TDRK to keep short. So two-derivative is just slightly different because it includes a second derivative to make it more accurate. So based on this tree, so therefore it leads to my research objective. So I'll be proposing a special type of TDRK methods, which is called improved TDRK. So as the name goes, improved two-derivative means that it is two-step while also incorporating the second derivative at the same time. So it would be two-stage fourth order and three-stage fifth order. And then after we have developed the methods, then we will analyze its linear stability by looking at the stability region, and then we'll analyze its numerical performance. So we'll compare it with existing Range-Kutta methods and the TDRK methods of similar order. So there are many authors that I've cited in my report. So I just want to highlight these four authors because these four authors have applied different the concept of second derivative and multi-step at the same time to, but not Range-Kutta, other kind of numerical methods. There are two derivative and multi-step, and all four of them have emphasized that this concept, these properties are able to give much more significance when solving ODEs that are stiff. It's still better for just ordinary ODEs, but if it's stiff equations, you can see that it is much more significant. So we can see this later on when I'm talking about my numerical results. So for methodology, so we'll talk about the construction of my methods. So because we're incorporating a second derivative for solving first order ODEs, so we have to find the derivative for the first order. So this is the second derivative. And then this is just the general form of a two-step TDRK method. So if we don't look at this part, it's basically just the classical Range-Kutta method. And then if we don't have the -1, so it's only single step, then it would just be two derivative. So if you don't have all this, it's just the classical Range-Kutta. So overall, it will become a two-step, I just call it improved two-derivative Range-Kutta methods. So as we can see that because of the summation means that there are multiple F evaluation and G evaluations every step. So we want to minimize the number of evaluation function. So I just converted the multiple F evaluation into just a single one. And then for G, we have BI and B negative I from here. Yeah. So basically BI and B negative I are all the same except for B1 and B negative 1. So to make it simpler, so I just factorize it out. Yeah, so this one starts from I equals 2. Yes. So just a much more simpler expression, just instead of G, I just replace it with K. Yeah, so K is just G function. It's actually the same. Yes. So for my study, we are only studying on the explicit form. So means it has a condition where any entries of A, where the row component is smaller than the column component, they'll all be 0. So it means it will be strictly lower triangular. Yes. Right. So my ITD methods will just involve single F evaluation and multiple G evaluations every step. So the motivation is to reduce number of function evaluations while improving the accuracy at the same time. So overall, my method is all derived. Before we find the coefficients, you need to have the order conditions. So all my order conditions will be based on Taylor series expansion. So I expand the first derivative. At the same time, I expand my methods. Then we compare the coefficients for the respective power of h. So if it's h squared, then the coefficient will be order condition 2. Then order 3 will be h cubed, and so on. So because mine is up until 5th order, so that's why I derive the conditions till order 6. So this is the one that we have. Yeah, so based on all these order conditions, then we can find our coefficients for our respective methods. Yeah, but before that, sometimes we may find, when we're solving for the coefficients, sometimes there might be 3 unknown parameters. So to solve it, we may use a certain kind of simplifying assumption called the Nystrom-Rowe assumption. Yeah, to give us much more number of equations so that we can solve the 3 parameters. Yeah. So I have 2 methods, right? So the first one is 2-stage 4th order. So it's 4th order, so we will use conditions up to order 4. So from there, we will get a system of 3 nonlinear equations and 5 unknown variables. Then we can get a by using the simplifying assumption, we can get a solution with that's in terms of 1 free parameter C2. So to select the parameter, we will actually minimize the error equation of the 5th order condition so that we can minimize the error norm. So this is the error norm of order 5. So just use by using Maple, we minimize, we can realize that the error equations get the minimum value at C2 equals to 31/60. Yeah, so we just substitute this value back to all the solutions just now. We can get all the values for the coefficients. Yeah, and then just substitute it back to the error norm. We can get the global truncation error for 5th order. So similarly for 3-stage 5th order, so we will use up until order 5, and then we can get a system of 5 nonlinear equations with 9 variables. Yeah. So then we can get a solution with 3 free parameters actually. So it will be A31, A32, and C3. So it's a similar approach. We just minimize the error equation of 6th order, yeah, to select the correct parameters. And then from there, we can get the error equation with the minimum value at these particular values. So we just substitute it back all to the solution just now, so we can get all the coefficients. Yeah. And then similarly, we just put it back to the error norm to get the global truncation error. So this is the construction of my methods. Yes. So like my research objective, then we will look at the stability analysis. So because we want to study the linear stability, so we have this particular test problem. So y prime is just replaced with lambda y double prime is lambda square y. So by just replacing lambda y and lambda square y into the equations of yn plus 1, and then yi and y negative I, so we can, in terms of matrix form, we'll get this. So y hat is just the matrix of values for y negative I. Yeah. And then with v equals lambda h and these two, we just substitute it back to yn plus 1. Then we'll get all these. So all these are in matrix form. So, but from here we can see that there's bt and bp hat. Yeah, b transpose hat. So b is just a matrix for b1 to bs, depending on the stage. And then b hat is for b negative 1 to b negative s. But as I said just now, bi and b negative I is the same except for b1 and b negative 1. But if you look at the second order condition, it actually gives us that b negative 1 is the same as b1. So we can just assume that b hat and b are exactly the same. So instead of just writing b hat, we just make everything in terms of b. Yeah. So this difference equation can just be replaced as, rewrite as a form of matrix. So we have this. So yeah, where we have mv. So it's actually the same, but it's just in matrix form. It looks nicer. So mv is actually called a stability matrix. And then we have a stability region defined as follows. Yeah. So lambda is just eigenvalues. So just replacing yn and yn plus 1 with the following symbols, and then we move all the from the right hand side to the left hand side. Yeah, so from here it's actually this one. Yeah, there's everything from here actually just replaced to here. Then we can actually get this with the eigenvalues and all. Yeah, so we can get the stability polynomial for ITD RK4 and 5. All this is gotten from by using Maple to help me compute. And then we can actually plot the stability region. So we can see that the fourth order has a greater area. We just look at the dark part, and the fifth order has a slightly smaller area. So these are the intervals that they span. So numerically, we can also see that ITD RK4 has a greater range than ITD RK5. But generally, stability region for numerical methods, higher order, we should expect greater areas. But our method seems to show a small contradiction because our lower order has a greater region. But it's actually not a very huge issue because convergence property is not equivalent to stability. So convergence just means that as the time step h gets smaller and smaller, the error should get gradually smaller. Yeah. So a smaller stability region just means that if the time step is slightly large, the error might be very large as well. But as long as the time step gets smaller and smaller, the error gets smaller, it's still converged and the method is viable already. So although it has a smaller stability region, it doesn't affect its convergence property. So it has been supported by Dahlquist. So he has actually made a statement before saying that convergence and the stability is not equivalent to each other. So then we will carry out our numerical analysis. So for our proposed methods, we just compare with some existing methods that are similar and with similar orders. So ITD RK4 and 5 is our methods of two-stage fourth order and it should be two-stage fourth order and three-stage fifth order. And then RK4 and RK5 is just the classical Runge-Kutta of fourth and fifth order. And because ours is two-step, so we also compare the two-step method, so improve RK method of fourth and fifth order, and then also TDRK 5 and 6. So TDRK 5 and 6 is actually a two-step, two-stage RK methods. It's actually similar to mine. It's also two-stage, it's also TDRK, but theirs is derived from using rooted tree conditions, a simplified rooted tree condition. So some of my order conditions with complicated terms, they actually just omitted for simplicity. So that's why our results is slightly different. They don't have fourth order, so I just compared their fifth order and sixth order with mine. So at the same time, we can see whether our methods, how does our method perform compared to a higher order. If it's better, then it's good. So we have 6 different types of first order ODEs. So we'll test our problems with these equations. So we have problem 1, problem 2. So problem 1 is just a non-linear first order ODE. Problem 2 is an oscillatory problem. And then problem 3, because we want to show the significance in stiffness as mentioned in the literature review. So that's why problem 3 is where we can, different kind of value of lambda, we can change the stiffness. And then problem 4, we start to have a system. Problem 5 is similar to problem 3, where it's just a system and we can alter the stiffness of it using different values of lambda. And problem 6 is an application question. So because it's an application, it doesn't have an analytical solution. So we have to approximate the solution by using RK4 method, but with a very small step size. So it's just h equals to 0.001. And because ours is two-step method, we only have y naught, which is the first step. So we need 2 steps, so we actually need to use RK4 to approximate the starting values as well. Yes. Right, so this is the results of all the problems. So problem 3 and problem 5, you can see that there are 2 graphs. It's because they have different values of lambda. One is when it's stiff, and when it's non-stiff. Okay, so in terms of overall, the pink one is actually IRK5. So somehow they just perform the worst. And the gold line, this gold line is actually the TDRK6. So only for problem 1 to problem 3, the first graph, TDRK6 has the lowest error. So it's actually error against time, computational time, so it has the lowest error. The green one is our ITD-RK5. So except for these three graphs, all other questions, for all other problems, they actually have, my method is actually either performing similarly to ITD-RK6 or it is better than it because some of the graphs they are lower. Yeah. And even though we are not better than TD-RK6, it shouldn't be an issue because they have higher order. So they should, it's not surprising that in some problems they have better accuracy than my method. And overall we can see that all of the methods, their error gradually decreases as the time step goes smaller and smaller. So they all have convergence property. So this justifies that stability region doesn't really affect the convergence. Yeah, and so, sorry. Yeah, our ITD-RK method has the highest accuracy. So for problem 3 and problem 5, you can see the stiffness of it. So lambda equals -1 and lambda equals 1 is when they are non-stiff, and then stiff for the other two. So you can see when it's non-stiff, the other methods, especially for problem 5, they actually perform quite similar. We are just slightly better. But once it becomes non-stiff, all the TD-RK methods, two-step TD-RK methods, are all performing significantly well. So it shows that a two-step TD-RK methods all have greater significance in solving stiff ODEs. Yeah, and problem 6 is just an odd one out because for this case, the RK5 method, the classical RK5 method turns out to perform the best. But we just assume that our theory is that, our hypothesis is that because the problem is non-stiff. So if it turns out to be stiff, then RK5 method might not be suitable anymore. Yeah, but our methods have lower number of evaluation functions and the RK5 has 6. So computationally, ours is much more efficient as well. Yeah, so these properties, yeah, because having extra grid points and two derivatives actually just makes it much more suitable for stiff equations and gives it much more higher accuracy, so and lower truncation error. So because we have these properties, it's not surprising that our methods have the best numerical performance. So overall, our methods have higher efficiency than existing methods. Competitiveness is because it is a class of multi-step method, so it's also competitive in solving mildly stiff problems. Its only drawback is because of the complexity of the function. It causes them to have longer computational time, and it has a relatively small stability region. So it just means that if the step size we set is too large, the error might just be uncontrollably high. But as the time step goes, the step size gets smaller and smaller, they will still just get very low error. Yeah. So the future works is just suggested that ours is explicit form, so implicit methods can be investigated because we can get higher order for implicit. And then to solve specific functions like oscillatory solutions, then we can use certain kind of fitting techniques. We can adapt to our method to make it much more viable. So these are all my reference, and yeah, that's all from me. Thank you.
Could you go back to the conclusion?
Conclusion. Yeah, all right.
Okay, so the proposed method, you say that they have higher efficiency than existing methods. So I think it's not completely true, right? Because ITD-RK4 showed the best result for, I think for problem 4 and problem 6 only.
Problem 4 and
You can go back to the graph.
problem 4 and 6.
But
Yeah,
I did not-
our methods, the ITD-RK5 overall performs the best or similarly well.
No, I think only for certain cases because
Except for problem 6, I guess. The rest, they perform quite well because we assume problem 6 because it's non-stiff. Yeah, the rest it's.
so
We compare with similar orders, like if it's the green one, we compare with all the because it's order 5, so we compare with all the order 5 methods. And then if it's IPP-RK4, I compare it actually with all the 4th order methods. So
Oh, okay.
yeah.
But you include them all in the same graph.
Yeah, I include them all in the same graph. Yeah. If not, it would be too many graphs, I guess, to leave it to 2 sets.
Okay. So the picture is not really clear. What is the
yeah.
the y-axis? What is the?
Oh, this is actually the log of the error, logarithmic value of the maximum error.
Which means that as the error goes to 0, then you have more negative.
Yeah, so the lower it is, then the lower the error. Because if not, the values will be negative 0.00. It's very small. So that's why I convert it to log, so it's easier to see.
So what is the x-axis?
Computational time. So that's why from here we can see that our methods generally have very long computational time compared to these other methods.
Computational time.
Yeah, computational time. So if you run the code, actually they run a few milliseconds longer than the other methods.
Yeah. So now it's computational time, but you just wrote time there, I think.
Oh yeah, I just wrote time.
And during your presentation, you say there is a time step.
Oh no, I think because all these points are like this is for time step h equals to 0.025, I think, and then 0.0125 and then 0.0625. So different. So we compare each dot, at the same time.
How do I know if you didn't mention in your thesis or your presentation?
Because my thesis I also included the table of values. Yeah, in my thesis I actually included the table of values first. Then I say that according to all the table of values, then I plot the graph. Because I think it's not so suitable for me to just put all the table of values
No,
here.
I think you can modify the picture, but
Oh,
means that
okay.
if I have to see the picture and also have to refer to the table, so it's okay.
Oh, okay.
And then
Maybe I'll just mention it in the thesis properly. That every dot is for different time steps. Yeah.
Yeah.
Okay.
So actually, it's I think very good, well written thesis.
Oh,
Except the list of references.
Yeah, I think because it's actually I use the Mendeley the form, but sometimes if I just edit one thing, then the whole format will just reformat. So sometimes if I always have to like make sure all my thesis is complete, then last but not least, then I manually re-edit the reference. If not, they will just revert back to the even the font will change. So yeah, I don't know why, but that's just how Microsoft Word just works.
What I mean is not the format, but it's actually the details. Like the page number is not there. The page number of the journal is not there.
Oh, okay. Oh, okay.
I
I'll
don't know
try.
whether it's a journal or it's a book. I don't know.
Oh, okay, I'll try to just pay attention to that. Yeah.
But yeah, I think this is.
I have a few questions regarding your results. So,
All
I
right.
see that you don't come up with conversion test. Why not you test? You plot your answer and compare the exact solution. Can you do that? Meaning that you need to adjust the exact solution.
Actually, all my
And
values.
then you plot the solution and you compare with your
Oh, all right.
solution, so that
Okay.
you can convince me that your solution indeed follow the same trend.
Follow the trend of the.
solution.
Oh, all right.
For the case, the models that have the exact solution, can you do that?
Yeah, I think I should be because most of the questions have exact solution already.
I think you should
Yeah.
in order to cover the part that you have not.
All right. Yeah, I think I can do it. Yeah.
But the plot is a error plot, right?
Yeah, it's an error plot where I compare it with I take the approximation from all the methods and then I deduct from the exact solution.
Yeah.
Yeah, it's actually the exact answers. Yeah, I get the difference of it.
I think you should put the formula in the thesis. The formula for the error.
Oh, okay.
And then let me see. I have another question.
I want another question
Oh,
regarding the parameter V in the
Oh.
stability test.
yeah.
It's very interesting because the V is not a real number, right? The V, the stability.
Oh, yeah.
region.
This V, right?
Yeah.
Because lambda H is just a
V is-
constant.
V is a real number or imaginary number?
It can be imaginary, I think, because it depends on the. Because lambda is actually the eigenvalue, so it actually depends on the eigenvalue. But because it's not a matrix, it's just it's just a value itself. So I just, because if not, there will be too many lambda H in too many unknowns. So just to simplify, just make it V equals to lambda H. But V can be imaginary depending on the eigenvalues. Because I think I read some papers, I think their eigenvalues turns out to be imaginary, but for my case, they're all real, I think.
Because if you go back to the stability region plot,
Oh, yeah.
it's actually the plot of
Yeah.
shape
Mm.
on the complex plane, right? Because
Yeah.
I have
Imaginary
real value and imaginary value.
dekat table tadi,
Right.
dekat graph
V
tadi.
is complex
Yeah,
number.
this one.
Imaginary
Because this stability region is plot based on the stability polynomial. So I think when you find the roots of it, there might be imaginary roots and real roots as well. So that's why when you plot it, there will be it will be on the complex plane because there's imaginary roots and real roots.
So okay, go back to my
Oh, yeah.
question. Ideally, I would like to know that from the stability region
Alright.
test, can you recover the parameters, the parameters that have corresponding to that region? Can you recall the parameter that will reside inside the stability region, so that you can verify whether your optimal parameter belong to that set? Can you do that?
I don't. Maybe I'm not very sure because if not, that means because all these stability region is based on the parameters that I've gotten. I'm not sure whether I can do that or not because without the values of A and B, I can't plot the stability region as well because the stability region are actually all plotted. This is just the general form, but for our method, so like for IPDRT4 itself, it has its own matrix, and then you put in the corresponding coefficients B, A, and C. So I think you need the coefficients to plot the stability region. So if without it, I don't know how to recall it back, I think. So I think the stability region is based on my values. So I don't know whether I can base on the region and get back the values or not. Because it's not a general region, it's just a region for the coefficients that I have gotten. I don't think I can recall it back.
But I think it indicate for the certain parameters, the solution will go diverse because it's unstable or something will happen.
Yeah, because from the stability region we can study the convergence property. Actually, I think I didn't mention in the thesis. I just wanted to add on later on when I just re-edit. So actually, for some of the problems, right? I think a few of problems, it's not I think problem 1, problem 2, and problem 6. I think all the time steps the same. We start from h equals to 0.01, I think, then 0.02, 0.05, then 0.025. But for some questions, I cannot start from 0.01 because for them, maybe for those questions, the time step is the step size is too large already. So I actually need to use very, very small values. I have to start from h equals to 0.00625 first. Yeah, so I think that supports that because I have a very small stability region, certain problems might require them to use a relatively small step size. But I didn't mention that in my in my report, I think. Yeah, so I think I want to add it on later. Yeah, it's when I start to explain everything, when I rehearse, then I realize, oh, I think I can add this in the report. So, because I didn't say what H values are used for each problem, so I think I will list it out in the report. I'll add it on later.
So maybe at the last,
Yeah.
the last concern that I have.
Yeah.
If you go to your coding is very simple. When you put we call it this component in the parameter solution. The component for the parameter solution. So
In the appendix, is it?
for the case ITGRK4,
Yeah, okay.
and then after that you include equation 1, equation 2, equation 3, and then the last one simplifying assumption equation, right? And then you use the solution function to solve everything and then come up with the optimal parameter. So this function is
No, I think I did I think there's one minimize function. Actually, I gotten the solution in terms of just C2. In terms of C2, then I get an error function. I define an error function, and then I substitute it inside, and then I minimize the error function. Yeah, I think my code is like that. Yeah.
So the solution function really corresponding with your methodology.
My source.
Your methodology, the writing that you mentioned in your
Yeah. It's actually all the same.
use the Taylor series. Actually,
I think I didn't include my Taylor series code in the appendix because it's very long, but I can include. Actually, in my code, I did start off with the Taylor series of Y, and then my method, the K1, K2, K3, I expanded, and then I actually compared all the Taylor series. You can actually see the for H and H square, H cube, what are the coefficients, and then you can solve from that. So yeah, I think I'll add it in the appendix because I did do it myself in the coding, like use the code to help me expand the Taylor series. So it's very long because I think I derived until K4 or K3, so it's very long. Yeah.
thank you for your.
Sorry, I have to cut the question and answer session since we already 30 minutes late. Okay?
Alright.
Thank you,
I think that's
Dr.
fine.
Ami.
Thank you.